All right. Um, so let's go ahead and get started. Everyone, welcome to join the IEC.
No, you get a cut off again.
Today we have Dr. Wei Xiong from University of Pittsburgh joining us. So Dr. Xiong is currently the director of the Physical Metallurgy and Materials Design Laboratory, and he is also the William Kepler Whiteford Faculty Fellow at the University of Pittsburgh. So Dr. Xiong's primary research area focuses on the computational material science, and with this particular talk, he's going to give us some idea about the use of calculation of phase diagram-based method for integrated computational material engineering for additive manufacturing. Dr. Xiong is the serves in the multiple committees in material societies, including the SAM International Alloy Phase Diagram Committee and 3 TMS committees, including the High Temperature Alloy Committee, Additive Manufacturing Committee, and Alloy Phase Committee, in which he also serves currently as a chair. And he also received a number of very prestigious awards, including the calculation of phase diagram Young Leader Award or CALPHAD Young Leader Award, TMS Early Career Faculty Fellow Award, and NSF Career Award. So with that, I think I'll hand this talk over to Dr. Xiong. Please.
All right. Okay. Thank you. Thank you very much. Can you see my presentation slides well?
Yes.
Oh,
Yep,
okay.
it's showing up.
Good. Thank you. Yeah, I just let everyone know I have two screens, and probably I was, look one screen on the slides, another screen on the on the audience. Okay. And feel free if you want to turn on your camera, right? So I can speak with some of the, you know, virtual audience, feeling not talking by myself, right? And
Okay,
then
I'll do that.
thank you. And thank you very much for giving this nice opportunity for me presenting our research. And my title is Materials Genome, ICME, and Additive Manufacturing. So right now we have the Physical Metallurgy and Materials Design Lab doing all of this research and focusing on advanced manufacturing. So I'm kind of lumping some of the highlights of the research, and these are the funding agencies that are supporting us with this kind of research. For talking about the research focus in our lab right now, we have mainly focused on three parts. So one part is thermodynamic modeling and database development. So this is the one that we are focusing very much on the materials informatics. So we know the importance of the database. We know some of the high throughput calculations is very important. And material science is a kind of science part lacking of data. So we want to making sure that we have enough data. Nowadays, popular with machine learning techniques and so on. Second part is the CALPHAD-based ICME, integrated computational materials engineering. And we do realize, the data has to be also calibrated, especially from the modeling, calibrated through the experiments. So we focus on some of the high throughput experiments, and I have an example that we did before with additive manufacturing. And certainly, based on these two important parts, we would like to develop some new alloys, some prototype alloy, and study the microstructure mechanical performance relationships. And then we focusing on different type of advanced manufacturing technique, and 3D printing certainly is one of the major focuses. For the CALPHAD is, the method of computational thermodynamics and diffusion. I will introduce the CALPHAD first and identify, where our position is standing and why we come from the additive manufacturing. And just another few words about our research lab. So we do have different facilities doing the additive manufacturing. We have the DD with both powder and wire. Powder is a little bit, several years already. So we are trying to look at chance where we can get a new one. So for the X1 is a sintering method with additive, and we have this NC's additive manufacturing center, and actually how this all of these machines. And certainly EOS machine is one of the heavy workhorse to produce some of the powder-based 3D printer jobs. And then we do a lot of things with the computation. We sometimes use atomic level simulation, such as like DFT calculations, but mainly we focus on the phase level computation using the SumCAC software. We also develop some of our in-house database, not only just limited with a conventional database. We do try our best understanding the phase transformation happens with microstructure evolution. Therefore, we study the quenching dilatometer. Quenching dilatometry were giving us some of the information, especially for this modern static transformation in the steers, and then the DSC measurement, thermal analysis, and the suction casting is a very important one for us to produce some prototype alloys. So these are our own lab facilities. So for the CALPHAD, first, what is a CALPHAD, right? So CALPHAD is a short name, so-called calculation of phase diagrams. So we focus on the computational thermodynamics. Talking about phase diagram, I think if you're talking about material science, originally, if you're talking about metallurgy, so we're dealing a lot of, the phase stabilities. So different alloys have different phases and fractions and stability. So we would like to understand in order to design some alloys, especially also dealing with the post heat treatment. Therefore, we consider it a map of materials design. And nowadays GPS is popular, so we use a lot of tools like computational method. And then for the phase diagrams, I would like to say, experimentally you can determine the phase diagram. You can use different method. You prepare the alloy. You measure the phase equilibrium. For example, this is isothermal section of a canary phase diagram. You can prepare alloy, measure the tie line, measure how many phases there, define the phase composition in terms of the alloy composition. And certainly you can do some thermal analysis and doing the, the calorimetry, measure the heat capacity or heat content and some other methods. And therefore, once you're heating up the material, what are the phase transition happens. So for the equilibrium alloy method is basically, is a very tedious one. Go back to, even 10 years or 20 years ago, people still heavily using this, and certainly we still need this quite often. It's just like too tedious, and people probably have the tendency to study more with computation, but it's actually have some urgent need with this kind of method to continue. Not easy to find the supporting agency to study this. That's another kind of topic. So, but then you melt the sample and section this, and then do the XRD, measure the crystal structure, measure phase composition, use the SEM EPMA, and do the DTA, measure the phase transition temperature. And therefore, you can determine different phase diagram with the isosomal and vertical sections. Or you sometimes, just directly determine the microstructure and study the solidification microstructure. Therefore, what are the primary phase. And actually, for additive manufacturing, you use this this kind of things quite a lot. A lot of people probably heard about SHA simulation. This is kind of, the confirmation of SHA simulation, sometimes with a basic fundamental level of research. And then, the idea is, if you know an alloy, usually the conventional alloy has, at least 5 or 6 components. You would like to say, oh, at what temperature this will have different phases, and what are these phase composition? What are the property of this phase? Do you need to introduce, enough strengthening phase to making sure the mechanical performance is well, right? So without computation, you can do tons of experiments. You can enjoy life by, hard working for 5 years and determine one isothermal section. Nowadays, we don't ask students to do this anymore, And of course, again, one part of the reason is not because this is too boring. Some interesting stuff also can come, but this no longer kind of the idea working with the fundamental ones. Instead, people were thinking about doing some diffusion couple, for example, right? So you have an alloy here, maybe pure nickel, and you have another nickel aluminum binary intermetallic compound, and then you put these two metal together, right? So and then you start to diffuse the composition by placing the alloy into the furnace at high temperature, and different temperature you will be able to measure the different phase composition, and therefore you can construct the phases, the phase diagram. And certainly, you can do a little bit more magic stuff. You place these three together, and then A and B, you will be able to understand the AB binary, AC binary, and BC binary. At the chip junction, now you're starting to develop a phase diagram with ABC. So this is kind of fast way. We call it high throughput as well. So JC is one of the colleagues also in the CALPHAD community. He did quite a lot of experiments. He once he was at GE, he invented this kind of technique where we call it diffusion multiple. So basically, you can put in a lot of different combinations, and then each triple junction you start to determine the ternary phase diagram. So that's a kind of smart way that you can use one component, alloy component configuration, and then determine different isothermal section at just one time, right? So different temperature. And certainly, very important thing is you are developing such a kind of phase map. Therefore, you can do some nano indentation, some of the the small scale property testing, and understanding what are the phases detrimental, not just do the measurement of the phase diagram. And sometimes you can also determine the diffusion, right? So diffusivity. So you can actually do different time and see how the composition profile develops, and then use a mathematical way to just try to extract some of the diffusivity as a database, like a CALPHAD approach. So that's another way to understanding the diffusion kinetics. So anyway, these are all the methods available so far. You can do the experimental determination of the phase diagram, but then how about you can extend something further if you want to do multi-component. Sometimes it's impossible. We cannot only deal with the ternary and the binary system. So two solutions is one, more effective experiments like what I said with the high throughput. Another thing is with the computational tool. So CALPHAD is kind of method dedicating for the computational thermodynamic diffusion. So what is the advantage of the CALPHAD? I don't want to discuss a lot of things with the CALPHAD, but then itself. But then I just want to show you some of the advantages. So go back to 2007, 2006. I was studying aluminum nickel silicon alloy, and went to University of Vienna in Austria. And then there is a world leading group doing the experimental measurement of the phase diagram. They did a lot of measurement and try to figure out what are the vertical sections, temperature versus composition. So they have no idea. Even they get the thermal analysis signal. But then I was doing the CALPHAD, taking all of this experiment data, not only just one. So this is one of the measurement that they did. So taking all their measurement and then do a CALPHAD optimization. Therefore, using the CALPHAD database, we take in limited experiments, but then we can extrapolate under the thermodynamic laws. So all of the relationships between the solid and liquid can be well identified. So even the top level researchers in experiments, they are struggling with how to identify all of these relationships. Another thing is like, if you do the uranium, neptunium, plutonium stuff, you don't want to do experiments anymore, right? So even the national lab, don't want to touch a lot of, this very simple, sort of simple, but then important binaries, right? So, and this is one of the examples we did before in 2013. So uranium zirconium, as you can see, a lot of people do different experiments, but then they're hard to identify what are the phase boundaries there. So you can utilize all of these phase boundaries to do a CALPHAD computation, and then the CALPHAD computation will be able to tell you exactly what are the phase boundaries. And of course, I have to say, if you do the CALPHAD, you have to making sure that this is something that you can make a judgment about experiments. If you have no idea about experiments, that's a problem. You make a wrong judgment about experiments. So that's the reason why our lab not only just do the computation, but we do heavily with experiments to study all of this phase transformation phenomena. And then another thing is like, CALPHAD is not just like reproducing the data. So if you have a good analysis with uranium zirconium with a phase diagram, and you can actually predict thermodynamic property. For example, like this, right? So let's look at the right figure. So you have two different experimental set, right? So one is this diamond, one is this star, right? So if you have no idea, you never do experiment before, what the best option for you to choose the experimental data. Either you're confused, you have no idea, or you may be charged, oh, maybe one of the group is a leading group in this research field, so you want to pick up that one, right? So, but then also another option is like make the average, but I can tell you making an average is probably the worst choice, right? And then if you have the CALPHAD to guide you to make a choice, this is a choice, right? So you can choose the year 1989, right? So this is actually the correct way to do the extrapolation and prediction. So CALPHAD has been utilized not only for the fundamental, so quite a lot of companies, I would like to say, I'm rather confident, right? So they use a CALPHAD approach. They are not necessary to tell people that they are using the CALPHAD approach. They have their own CALPHAD database development, and they want to hide because they don't want to let people to access this kind of method. But then, you know, fundamental CALPHAD assessment is very important because you buy the commercial database, you are not allowed to change the database parameter. So for the companies that I know, for just taking example in Sweden, right? So because I got a degree there in Sweden, and then Sandvik, you know, Outcomp, all of these steel companies, they have their own database besides the Thermocat conventional database. By the way, Thermocat is a spin-off company before at KTH. So at KTH we developed this kind of software. Nowadays it's very popular to use this software to do different things. And then this is kind of, you know, the experimental, sorry, the computational. And as you can see, very complex steers. And then you have to decide what are these heat treatment choices. So without all of this understanding of the phase transition, you are actually just hitting in the dark. So there is no way that you can propose such a kind of solution for the post-heat treatment of the steels. So I would like to say CALPHAD is not necessary just, you know, for the computational thermodynamic diffusion, but also nowadays it become more and more popular with precipitation strengthening, which is one of the most strengthening mechanism, one of the most important ones in the materials design. So they have this, you know, the Thermocat, and then went to the DICTRA, which solving the problem of diffusion. And then 2011, they start to develop this TC Prisma can solve the problem of the precipitation. And nowadays, using the CALPHAD type of database in such a kind of CALPHAD type of software like Thermocat, people can predict the thermodynamic properties, or sometimes even the physical properties, or even the strengths. So you can actually write in the physical metallurgical model or mechanical metallurgical model based on the multi-component thermodynamics, because you can have a lot of different models, but all of these models probably just solving the hypothetical system thermodynamics. So you never can have a good chance to get a good realistic prediction. Okay. But of course, you know, some models is actually a heuristic, right? So you can get some understanding of the mechanism. That's a different thing. But I think, you know, I take Greg Olson's quote and rename it. You know, CALPHAD was computational calculation of phase diagrams, but I think people are already doing this calculation of phase dynamics. It's not necessary for the stable phases, but also including the non-stable phases. So just people have to make a right choice with the different models. So the CALPHAD is really, you know, a kind of way we think belongs to materials genome. So you have to develop such a kind of database, making sure you're understanding the alloy effects if we're talking about physical metallurgy. And then you went a little bit higher to the ICME. So ICME lumping different model together from the processing to microstructure to property and make a prediction. And very important thing, I think people has to pay more attention about uncertainty quantification. That's very important part nowadays, and especially dealing with additive manufacturing components. Later on, we also have a discussion about this. I think Materials Genome Initiative, probably a lot of people, you know, heard about this, and NSF has such a kind of program called DMREF. It's based on this kind of concept, Materials Genome. So this is our viewpoint about the CALPHAD. So CALPHAD can link with different atomistic modeling, and then because CALPHAD dealing with larger scale, but of course nanoscale, we can also do some of the modification of the models, but also, you know, kind of tentative ideas about some of the macro scale thermodynamics. And then you also need the experiments, right, to support. Otherwise, garbage in, garbage out. That's not a good thing that you want to look into. So for the concept of materials genome initiative, I think we have the computational tool. We care about the digital data, the database, and we also care about the experimental tools. Right. So what we are doing, with materials and manufacturing design is really based on this so-called systems design chart. So this chart will lay out all of the important components for different stages with processing microstructure and properties. And of course, for mechanical engineering, also talking about macrostructure. And I know some of you folks doing the lattice design. So this lattice is, from the 3D printing, you can also place in there, right? So, and the material science focus a little bit more on the microstructure level. And then we care about the linkage among different steps, right? So these are highlighting the most important factors from different processing to the microstructure. We do care a lot about microstructure engineering. And of course, if you're talking about design, it's coming from the performance and property, what kind of high property you want. And then we know what are the microstructure can be suitable, designed for this. And then you go chase back about what are the choices with processing. Sometimes you have constraints. Sometimes you have the cost analysis. And for example, if you're developing steel, people don't want to put in a lot of niobium. It's expensive, tungsten, right? So even nickel is expensive, right? So there are some limitations we have to identify, but then based on the multi-component model, we have a better understanding, right? So we know the limitation of the design. For alloy additive manufacturing, I don't think I need to talking too much about difference regarding this, but then mainly saying that I would propose a general system design chart for additive manufacturing, and all of these middle parts highlighted is actually the microstructure engineering that we can deal with, either coming from the CALPHAD-based ICME modeling or fused together with experiments. Again, so we do heavily with experiments. I don't think it's realistic that nowadays we can just press a button and get very accurate results. So computation can guide us to do much better experiments with better choices. So for the microstructure, I think we care about the grain refinement. For the transformation toughening, we can dealing with a lot of stacking forward energy calculation, particle strengthening. We can use some of the tools like TC Prisma to predict the strengthening of the particle distribution and fraction. And then anisotropic properties. Sometimes you have to deal with the choices with homogenization, but also combined with recrystallization processes. And defect control, you have to consider some of the inclusion and carbides or oxides. And the cover modeling can also coupled with finite element modeling to understand the in situ process of the melting. And of course, different stages are becoming critically important regarding the inference of the microstructure. So I would like to divide the designing aspects into three different steps. One, we're talking about feedstock material. The other is additive manufacturing, and then the third one is the post-processing, including post-heat treatment and maybe sometimes surface modification. I would like to say this is very similar, like what we have a child, right? So you care about the quality of the child born, right? So I mean, how to design, I don't know, right? So it's a magic, but you certainly will not drink a lot of alcohol, right? So that's everyone experienced, right? So almost, right? So, and then, you would like to making sure that, go to a good daycare, right? So, but then, how to do the in situ processing, right? So, and then you would like to, send into a good college, right? So that's a kind of, the post heat treatment and post processing, right? So we deal with. Okay, so if I restructure this, right, so we have three different components, and each components will have interaction. And of course, we should never forget, this is a governing. So we do have the process, structure, property, performance, three links chain together, right? So identify all of these relationships. Let's take an example about feedstock design, right? So feedstock design is a kind of interesting story that we get this own Armani project funding. That's actually my first single PI funding. And we were so excited about doing this kind of research with HSLA alloy steel. We worked very hard and get a lot of publication and results for this one. However, we experienced a lot of, the difficulties in the beginning because everything's idea. I think this is the kind of common problem with people doing the additive manufacturing research. Before you do additive manufacturing, you think, oh, this is really, eco-friendly, environment friendly, right? So you just bring the powder and do the printing. No, I mean, if you choose the powder, you have to making sure that the powder is easy processable, and then printability is good, right? So we do 316 is okay, 718 is okay, right? So everyone is doing this, but now HSLA, no one knows. It's good for welding, we know. Then you can move forward with additive manufacturing, right? So experiencing some of the similarity with the thermal history. But then the challenge is, if you design the powder, this is the cost, right? So if you have minimum order quantity, right? So and then the price is extremely high. You have like nearly close to $200 per pound, right? So with DED, you really don't need to order like 200 pounds, right? So the issue is like the chamber cleaning the powder after you manufacture takes a lot of time, and then that associated with the cost, right? Even if you're rich enough, it's not necessary that solving the problem, because these people saying that they deliver within 2 months, but at the end we wait for more than 6 months, right? So if you want to design 10 alloys, right, so that's a nightmare. You have to put in both the cost and the time. And then quality control is also another problem. People say, oh, additive manufacturing is new, even though you have some experience in powder metallurgy, but not every material is good for powder metallurgy and test before. So they don't know what are the choices with composition uncertainty. Maybe they can just use in the similar things like cast alloy, but not necessarily these can be guaranteed as a good choice. So the idea behind this is we want to smartly spend the taxpayers' money in this project. And we want to making sure that we have a confidence to produce all of this powder composition. So if this is original cast alloy composition on average, you kind of deviate with uncertainty during the powder manufacture. So you probably in this range. But our idea is, can we try to identify a better composition range, a better optimized composition? Therefore, you shift this composition, even if you still have the same area, same uncertainty that you are, governed by the processing machine of the powder, but still you are actually located in a better area, that the powder is high in the quality. So with this bear in mind, right, so we develop kind of ICME model framework. So this model framework is building on the alloy composition and post-heat treatment. So you need to care about the post-heat treatment once you design the alloy. That's very important, right? So we use different models. We are not only concentrating on the CALPHAD model. Certainly CALPHAD model is one of the major part, but we also combine with machine learning model. We know some of the predictions of the MS temperature is critically important, BS temperature critically important, so we don't mind as long as we can make the prediction to be reliable. And we also use some empirical to test and evaluate the printability. We know some constraints of alloy composition. And then if you want to utilize all of these ICME prediction models, then there is a way not only just do the uncertainty quantification, but also if you want to further apply for the composition development. So it's the same idea. So basically, you can throw millions and tons of the composition choices and then go through all the simulation. Therefore, you develop different criterion of the judgment. Or if dBTT is low enough, if the strengthening particle is high enough, right? So with the content, or how about the printability? How about the toughness, right? So all goes, and then you circle around, and then you start to zoom in and shrink in the area of the alloy composition choice. So we have to identify the system design chart, that's for sure, and we want to specify all of these properties. That's actually ultimately very crucial and important, because if you have no idea about the quantities of different level, then you can't do a good design, that's for sure. Then it's kind of discovery. Discovery is totally different. And then we also care about the quality of the ICME model. You can build thousands of models, but we have two principles. One principle is such a model can be linked with multi-component cases. So that means the model should be based on the alloy composition choices. So you input one composition of the alloy with multi-component, more than 10 elements, you have to get an output. The second, you have to calibrate the model. The model in many of our case studies is not necessarily predict a kind of digital accuracy. I don't think that's actually something that we can do nowadays, even with machine learning, right? So all of this buzzword, I don't care. But then the thing is like, can we get a kind of design guidance? Can we get the model to tell us about the alloy effects? That's very important, Therefore, you have the prediction considered to confirm with the existing experimental data. So we calibrate the model using existing experiments. I have to say, not necessarily tons of data there, but more or less we think we should be satisfied by having this kind of comparison. Of course, this is just one part. We also compare with some other properties and predictions with the microstructure to confirm. Okay, so this is the main part, so-called high-throughput computation based on the CALPHAD ICME model. So we build that model. So this is the original initial composition with the range associated. So if you blind yourself, don't know anything about it, and just know this is HSA 100 alloy, and you tell the casting company and powder manufacturing company, and then they were going to produce this. But then, if you have such a kind of model, you can say, oh, let's fix the carbon content, from 0.02 weight percent to 0.1%. And then each being here on this figure, I just taken one figure as an example. It's not so difficult to understand. So, and then each bin means you fix the carbon content around 0.05, and then all the rest composition can be changed. You have a variation. So there'll be one bin contains all different composition of the rest, right? So you have a sampling size. You can choose either large or small depending on your computational capability, and therefore you have a tendency. So varying the carbon content, then you can see, oh, carbon around 0.065. Now you have higher chance to get higher yield strength of the final printing product if you get the post heat treatment correctly. So that's a kind of idea. And then certainly you further moving on with different criterion, DBTT, right? So ductile brittle transition, freezing range, and all of these, empirical printing choices. And then finally, you can get, some of the cases. So this is just kind of one example for one beam showing up here, right? So, and of course you can get in different, criterion sort out, and then mainly we focus on these four plot and 4 different criterions. And then these actually can lump together and do the further data analysis. Now you can see, oh, by changing the carbon content around 0.06 or 0.05, then you can see all the things are matching, right? So for example, this is a pink color, right? So on the bottom of this table, right? So you can see this all different criterion matches. So that means, carbon content 0.06 around is the best choice. And then you move forward with the rest. So you get the initial and then you get it optimized, right? So these two compositions different, is slightly different, but not dramatically, okay? But then you can see the difference. So taking example for here, you see this is a volume fraction of different phases versus temperature. So on the right-hand side, this is after optimization, copper cluster and M2C carbide are the two major strengthening particles. As you can see, at least for the copper, we can find a way within this range. We can find copper is actually can be potentially a little bit higher than the original one if you consider the cast alloy. So, and of course, you can sort of a virtual experiment say ideally if everything matches, then the optimized powder can drive to nearly 100 success of the printing. And then if you use cast ones, then originally theoretically you already failed with 50% around. And of course, experiments can tell everything, right? So computation is just digital. So what we did, we continue with the printing all of these tensor bars and Sharpie test samples with different notch opening position. And then a lot of portion I didn't cover, I don't have time to cover, is actually the heat treatment process, right? So we also need to design with heat treatment. We also need to use CALPHAD-based ICME to design the proper homogenization time and temperature and tempering temperature. These are all the precipitation strengthening particle related, the design aspects. And after doing that, and then you do the testing, right? So you have the good printability. We optimize the laser powder bed fusion parameters, like the hedge spacing, the diameter of the powder, and also associated with some of the layer thickness, everything that you can name. And we did it heavily, and then we do the good build with minimum porosity developed. And then after heat treatment, as you can see, this is a temper example as printed example, all are actually higher than our targeted performance with the yield strength. And of course, for HSLA used in Navy, it's very important to evaluate is actually kind of BCC type steel, and therefore is critically important for the DBTD value. So DBTD is overall lower than negative 20 degrees C. So we think this design is actually rather successful. And certainly once we submit the paper, right, so to the MPJ computational materials, and the reviewer says, why don't you do machine learning? Why you use high throughput, right? So like, okay, so you love machine learning, we can do machine learning. Actually, this is the highlight. So materials science, we don't have enough data. So therefore, you can use the curated database through the modeling. You can generate a lot of data. Now you are not lack of data. So you have reliable modeling, you generate a lot of data, and now you can do the machine learning based on that. I'm not necessarily an expert in machine learning, but we use different machine learning algorithms and identify, this is one of the best fitting with the experiment data. The advantage of machine learning is actually, rather than giving you a single choice of the average composition, now machine learning can help you to have a trade-off between the reliability and the performance. If you want to have a performance and yield strength and ductility to be very high, then your choice or the uncertainty of the composition can be very small, right? So the other part, if you have more tolerance with the performance, then you have much wider range of the alloy composition. So that's a kind of the trade-off that you can make based on the machine learning work. And actually, our online tool is now available, and you can test with some of the things that we did with machine learning. So the second part I would like to discuss about the in-situ microstructure engineering. Still a lot of things that we need to solve with additive manufacturing. Taking example of laser powered bed fusion process. And I think, still a kind of big challenge nowadays. Even this, I always bring these slides, starting my study of additive manufacturing in 2013. So, these are the experimental data, measure the thermal history. But the experimental measurement not necessarily be able to tell you exactly how the heating and cooling rate. So you rely on the modeling, and then you compare with the experiment. Okay, say, oh, this is a good understanding. Okay, so, but then the thing is like how to do the thermal modeling. A lot of people use finite element model. So in the year one, once we started, I approached to the mechanical engineers, right? So doing the finite element model. So it's actually very surprising to me as a materials people. And then all of these quantities are actually input for the finite element model. However, these are all constant values as a choice. It's not necessary. So if you know the CALPHAD database, we have the phase-based database. So basically, you have all of this information as a function of composition, temperature, and sometimes even time, right? So this becomes very useful as a kind of temperature and composition dependent, and you can fuse them together. So a quick example is what we did early on at Northwestern colleagues is, you melt the melt pool, you simulate the melt pool, and then on the left-hand side is without this alloy thermodynamic modeling, so just putting the constant value. On the right-hand side is with the thermodynamic values coming from the CALPHAD. As you can see, for the final status, you will get totally different size and shape for the melt zone. So that's become a problem because some people doing further, additional simulation based on this geometry. Then what you get is actually an error propagation. So the reliability will goes down, right? So dramatically, if you build on this. So another kind of interesting story that we continued just last year with JPL NASA is we did a kind of simulation based on the CALPHAD approach. And of course, we also collaborate with UC Davis. They do the thermal modeling like what I showed before. So in the CALPHAD model, you have equilibrium solidification, assuming everything happened in equilibrium. You can have DICTRA solidification. You can put realistic cooling rate. I say realistic, not necessarily quite realistic because it's hard to measure with the thermal input. But then we can take information from the thermal modeling of finite element. And then the third choice is shallow modeling. So assuming no diffusion in the solid, extremely fast diffusivity in the liquid, right? So you sometimes care about fast diffusers like carbon, nitrogen, right? So back diffusion can happen as well. So with these three simulations, like you can understand about phase transformations, and then how to evaluate the cracking, right? So this is kind of the whole flow chart. Basically, this part is something that I was telling you before, right? So you can read all the information from the CALPHAD or experiments, right? So with composition and the temperature dependent, you get a more reliable of the simulation for the thermal history. Now you have the thermal history. You can feed back to the ICME model, to the CALPHAD type of model. You can do the simulation, taking this thermal profile and do the prediction of the phase dependent properties, for example, like cracking. So here, what we have, the cracking model, is actually, again, based on the CALPHAD method. So in 2015, Professor Kuo in UW Medicine, he published a paper in Arctic Material, is very highly cited, more than 200 times now. So he developed a kind of simple model, not necessarily simple, okay? So this is actually a model where you require the input of the temperature gradient. This comes from the thermal model you can get. And then the fraction of the solid phase come from the CALPHAD. And then you can predict the potency of the cracking. So basically the idea is very simple. If you have this such a long channel developed through the dendritic structure, whatever, during solidification, then the liquid is hard to fill in, right? So, and then potentially with a lot of gaps here, and therefore it's easy to form cracks and pores. And then you want to have this gradient to be small, and then phase fraction to be, larger and faster to fill with these gaps. So that's very simple idea. But then, you can start to do the simulation modeling again. So we have two ways. You can put in every temperature as an input and then do the CALPHAD-based cracking potency evaluation. That's kind of tedious. If you solve the problem with a location specific, maybe you can do that. But remember, you have error propagation. So this model is not perfect. However, we did a kind of simple way to demonstrate this kind of idea. So you can find some representative thermal history from the thermal modeling, center of the melt pool, beside the melt pool, right? So, and away from the melt pool, right? So these three dots are actually always here. And then you can see the melt pool passes how the thermal history changes. And then you can now put in this temperature dt and associate with the fraction of the solid phase. And now you have the cracking susceptibility prediction. So now you have these different temperature choices with the CALPHAD modeling, right? So coupled with thermal modeling. And now here is the quartz model prediction. So because CALPHAD, the DS part here, FS part here, is actually based on the alloy composition, right? So now you can change with the alloy composition and say, oh, if I have an ideal case with aluminum copper, so if you think, you have more realistic cases like, number 3, the cooling rate is actually 10 to 5 K per second, right? So, or if you go a little bit higher, right? So this, idea models, right? So they are all consistent, like 1.8 or 1.5, or have the highest potency to develop cracking. But then if you, have some other choices lower a little bit, and then these 2% around copper will have highest cracking potency. So this is kind of, giving you a kind of idea that you can use such a kind of model to have the possibility to evaluate the cracking susceptibility, and based on the multi-components of dynamic and diffusion. So another thing that I would like to highlight is a design between the material science, manufacturing, and mechanical engineering. So we have a project that's through the NETL. It's already finished, and we actually have a project due in this month. And then the thing is, like, we are thinking about using wire feed additive manufacturing to repel some of the component used for the fossil fuel power plant. And then, very often used is a P91 steel. So how about repel P91 using P91? Sometimes not necessarily a good choice because 740H is high performance. so have high tolerance with the processing. Therefore, maybe you want to use a stronger material to repel the weak material, right? So therefore, the interface become a kind of challenge. You have to understand how to design the interface, right? And then if it's successful, maybe in the future you can have, the inside is P91, lower the cost for the component of 740H, right? So you can do different geometry and connection. It's similar like welding, but you have a lot of freedom to do with this 3D printing technique. So it's a kind of, the several year projects we run. And then this kind of basic idea I wouldn't be able to cover, but then the thing is like, we first evaluate the single print of 740H and P91, and then we go with the design of the gradient between the 740H and P91. For example, like this one, right? So the building part. And then you maybe have some other choices with different mixture of the alloys, right? And then we have this sharp interface gradient builds, right? So P91 and 740H. We're using the Jeffrey-Tech machine to print, right? So we have a Jeffrey-Tech just installed in Pittsburgh. Is kind of monster printer, right? So it's a very large component. And before installation, you feel this room is actually huge. After you install this, you think this is a little tiny room, right? So because the printer is too big. And anyway, so this is just one case study, right? So we have the sharp interface between the alloy A and B, and how to deal with the diffuse interface. And then in the very beginning, we start with the project. The question is, should we print P91 on top of 740H or the other way? So we find actually P91 print on 740H, you find this cracking very easily. But if you print the other way, you don't find a lot of cracking. But if I come from the metallurgical side, I will probably don't think too much about it. I will think about the microstructure level. And indeed, this can explain to some extent. You can find a lot of niobium concentration higher surrounding this cracking. And we still find a lot, even later on we study this kind of alloy. And we find niobium carbide is probably one of the cracking sites where you have the micro-void softening effects developed during the printing. But then is this the whole story? Certainly not. Why? Because we collaborate and working with mechanical engineering. Albert too is one of the faculty members here doing the mechanical simulation. So he has thermal model. We calibrate the model with the thermal history. We have the in situ, camera, and also embedded with the thermal couple to making sure the thermal modeling runs reasonable. And we have the mechanical model developed with a calibration using XRD to test with the residual stress. Now he has a residual stress model and thermal model. Now we make a prediction. So as you can see, thermal conductivity becomes critically important because the Inconel is 2 times smaller than the P91. So if you build in steel on top of Inconel, you accumulate a lot of heat of the printing part. The heat dissipation becomes very, very slow and very difficult. And then you further put in this thermal history into the residual stress simulation. So what is the answer? So in this model, you have UTS yield strength and the residual stress. As you can see, you print P91 over 740H, then the residual stress intensity becomes comparable with yield strength. But then if you print it another way, residual stress is always keeping as a lower part compared with yield strength. That's kind of another thing that you have to consider, because usually metallurgical person does not really consider too much about the influence of thermal conductivity and transfer to the residual stress. This becomes an issue. So with the sharp interface print, and certainly we also have a lot of things to study. And I also have to say, right, so with the material science level, for the diffusion interface also become interesting, because another thing is P91 on top of 740H, because accumulated heat, then you can see a very diffuse zoom with iron diffusion happens, but 740H on P91, you see the limited zoom. Okay, so at the end of the project, continue with the project, we always print 740H on P91, which is a good choice because you can use substrate with the steel and then print steel on steel and then print the Inconel on top of the steel. Okay. So what should we consider further with the next level with the post-heat treatment? Post-human is very interesting. I take a very short example. So we have Inconel 718. We did quite a lot with the NASA funding. We still continue publishing because really a lot of results. So one case study I show in here is comparison between cast and additive manufacturing example. And as you can see, we have suction casting. We use an arc melter to prepare the example and compare with as printed microstructure with the powder bed fusion. You can see the lab phase geometry is different. The morphology is different. Okay, the distribution is different. And then if you're checking under the EDS, the segregation along the lab phase, along the grain boundaries is also different. Okay, suction cast has much more pronounced concentration. And then this shows the capability of using the CALPHAD to guide you to design. Okay, you can complain. You say CALPHAD generate results with no sense because none of these predictions can be accurate. But in another way, if you don't have a CALPHAD approach, don't run the DICTRA simulation, you blind yourself. You don't know even how long time you should start at this homogenization temperature. But if I have this model, the model will tell me, okay, so generally saying cast require longer time, and the cast will require around 30 to 1 hour, and the additive manufacturing may take less time. So that's a kind of guidance that I can immediately start to design. If I use different temperature, what are the time that I should with the homogenization. But then the challenge is we can not really solve all the problems because the grain structure is also critically important. So this is also interesting study with this LPBF and suction cast. As you can see, for this inverse pole figure from the EBST, you see, you actually, do I still have a little time cover? Okay. All right.
Yeah, I think so.
Okay, so I will quickly wrap up some of the things here. So, but then, you have LPBF, you see, interesting. You have 1200 degrees C for 12 hours. You still keep very small size of the grains. But if you have the suction cast, you actually get very large grain size, and even sometimes you can call it abnormal grain growth. The reason is because the additive manufacturing actually initially in the as printed microstructure, we bring a lot of residual stress. This residual stress is not necessarily forming the crack, but is high enough as a store energy to trigger the recrystallization. So if you choose the proper homogenization temperature, then you can use recrystallization to refine the grains. So that's a kind of striking, and we feel so encouraged because additive manufacturing is not just a toy. You can get better configuration of the grain compared with traditional manufacturing processes. So for the ending part, I would like to say how additive manufacturing as an engineering tool can serve for the fundamental research in materials genome. So this is one that I, bring this back. So in materials genome generating the database, material science has a database problem. We don't have enough data. So we use traditional manufacturing to prepare sample and then do the diffusion couple. And then you can measure different, properties and phase information. And then some people would also use thin film preparation, right? So, and then you can have a gradient of composition and measure the properties as well. But then it's different with bulk, I would like to say. Additive manufacturing, as you can see, one method, if you have the DD, you can change the composition dynamically. You can print a lot of samples and start to study with different properties, with different composition combination. Another thing very interesting is you actually can go with the LPBF method. Even though it cannot change the composition, but it can guide you to design the post-human. We did a kind of example with 718 because we know the strength of the Inconel 718 alloy is at 718 degrees C, right? So therefore you can see we print a long bar. We have a broken furnace, right? So we should use that. So I put this furnace in the center and with the heat, but then I open the gate of the furnace, and therefore you forming a gradient temperature. And now with one long bar sample printed with 3D printing, and then you can measure a different strengthening at agent step at different temperature, okay? And then now you can evaluate the microstructure and evaluate the microstructure with the hardness and confirm 718 is the highest, the peak performance of this strengthening. So this is kind of demonstrating for the method of high throughput. And I have a YouTube video just talking about this kind of high throughput. I just posting here. But we have to making sure we understand the limitation. As I already showed, additive manufacturing has different regarding the microstructure in the as printed state. Therefore, if you compare, we did a systematic study, compare additive manufacturing with cast, as you can see. So 1 hour, 12 hour as printed microstructure, and further with the homogenization continue with the agent. The precipitation distribution is different once you look at the cast alloy. So if you want to solve the purpose for some fundamental research, for the phase diagram measurement, for the phase transformation, then you have to be very careful. And of course, the advantage is if you want to use this as a basic tool to design and solve the purpose for additive manufacturing, then you should be more comfortable. So overall, I think, these 3 parts are actually, corresponding to the core of materials genome and ICME. And I would like to finally say, we know all models are wrong, but we have to understand the limitation of the models. We should use simple model, but not simpler model to solve our problem. But we cannot wait. So we should integrate different models. And materials genome certainly can accelerate this kind of process for the design of additive manufacturing. Very important thing, we have to collaborate. We have to collaborate, and we have to understand we have some of the problems need to solve. Nowadays, material science, I still compare as a cooking, right? So you have rice and meat, you need to get all of this data, experiment data, simulation data, and you have to curate this data. You want to have fresh vegetable to eat, right? So you have to making sure the data quality is good, and you need to have a recipe, right? So you would like to care about the quality of the models. What are the models is useful for your design or for the discovery is different. And then cookers, right? So instrument and computational clusters. Nowadays, most of the time is not a big problem for us. So collaboration requires not just materials. So ICME in the original definition is integrated computational materials engineering. I would like to say M is actually stands for mechanical materials and manufacturing. So we need to work together with each other and cross the barriers and identify the knowledge gap. Thank you very much.
Thank you very much, Dr. Dr. Xiong. That's very, very interesting talks. And I know we're a little over the time now, but I would like to propose to, extend this a little bit so everyone has a chance to ask questions, because Dr. Xiong covered a lot of grounds with some very interesting projects.
Thank you.
I don't particularly have a question, but I do want to comment that I like the fact that you cover the whole waterfront here. I mean, from the fundamental modeling to the experimental, actually doing it in the laboratory. And you say collaboration is important, but it's also good that you can actually cover both ends in one laboratory there, or in one group. And so congratulate what you've developed, what's there in Pittsburgh. It's very impressive.
Thank you very much.
Well, I have a question or kind of comments. So thank you for the very interesting presentation. This is the first time I heard about a kind of a mechanical engineering talk about data, talk about the simulation from data perspective. So I do see a lot of opportunities as a data scientist. So especially for the combination of experimental data and the simulation data, I think the combination will not only help us understand the material properties and the propagation of that property to process and to quantity, but also help us understand how the uncertainty quantification can be used to propagate the uncertainty and further allocate uncertainties among the full stream process, from material preparation to process to the quality control and also the post-processing. Yeah, that's really interesting.
Thank you very much. Yeah, we still have a lot of things to do, I think. Yeah, this is uncertain quantification, even we're talking about printing different printers, right? So what are uncertainties, right? So
that's right.
Yeah, exactly.
That's right. The heterogeneities really exist in along the process and also the material preparation, and how to quantify the uncertainties for different processes and different machines, this is also important. And this is part of the transfer learning efforts happening in data science world.
Right, exactly.
So jumping in here, I have I've been thinking while you were talking about, how this model, how this the phase diagram, the entire phase diagram based approach that's very fundamental can stretch to so many different areas. In your opinion, what do you think about using this utilizing this same approach for some of the microstructural predictions? Say if I wanted to generate certain texture, maybe not even just phase, but I wanted to have certain, certain green size range and certain alignment, certain green orientations. What do you think about the maybe the limitation or potentials for this approach?
Yeah, I think that's a beautiful question. And materials microstructure engineering consider mainly two parts. One is phase level. So at the phase level, CALPHAD accumulated, several decades experience. We learn more, and then we learn the knowledge gap, can identify that. Usually that's related to the metastable and unstable phases. If you're talking about extending to the second part, is the grain structure. So grain structure is even more challenging. One of the fundamental challenge is still going back to the thermodynamics. So right now in the community, especially with CALPHAD, even though people worked quite a lot, but then we do see there is a fundamental model gap there. So John Kahn, in his times, he did some initiation of the vector space thermodynamics. So, if you're talking about different, crystal orientation, you have different, vector associated with thermodynamics, right? So I don't think the heterogeneity of the thermodynamic models is available. And then this is certainly more complicated. It's not only related to the model itself, but also it's also related to the development of the software. How people can make such a model to be able to easily implement into the software. That's a kind of big challenge here. And I have to say, because we sort of, satisfied with some of the achievement, Metallurgy has already developed, so long time. So we know what are the dirty place. Sometimes we don't want to go there, right? So for the grain structure, I have to say, we also have the tools. One straightforward tool is not necessary that I say this is the golden tool yet, because still a lot of fundamental models lacking, is, for example, like phase field. So in the phase field, one of the efforts is utilizing all the multi-component thermodynamic and diffusion to support these Kahn-Hilliard and Allen-Kahn equations. And then you can take the CALPHAD prediction into that model and then make a prediction of the grain structure. So people already studied. However, the limitation, I can see not only the model has a lot of problems. I know that because I also write my own code with phase field, and apparently I dropped. It's too difficult with some of the practical solutions. And then even if you want to do practical, for example, like multi-component, you have the problem of reading this CALPHAD database, okay? And then that takes a huge time, and then you need to making sure, figuring out some of the metastable, database accuracy, and still yet you have a lot of parameters in the phase field model, for example, interface mobility and so on, is not well determined. So you have some physical quantities that essentially go to the fitting parameter. So it becomes non-physical. You have such kind of dangerous things to solve. But then for the grain structure, also the thing is you end up with some of the scale problem. So for some of the people using the finite element method to do the phase field, the interface grain boundary is very interesting for material science. And then you have to create, maybe a lot of mesh in the grain boundary to resolve such kind of physical quantities. But then you end up a heavy mesh with the bulk. So some adaptive mesh and so on becomes a very hot topic with the fundamental. But I do see there is a gap. Bring this one into the simulation for the practical engineering, and end up with a lot of times. At least for my lab, we use a lot of experimental tool. So we get some heuristic understanding from the CALPHAD, and then we do experiment to confirm. Because even talking about recrystallization, you don't have a good recrystallization model, to be honest, right? So nowadays it's still a knowledge gap in physical metallurgy, right? And integration and scale it up, you start to have uncertainty propagation. So, but then CALPHAD is not necessary just for the simple phase stability, but if you're talking about the strengthening effects, CALPHAD still can solve some of the problem, not the whole. So for example, you can predict the size distribution and also the radius of the strengthening particle. So these can actually already good enough to contribute understanding of the ear stress. So that's a kind of mess. I mean, I just want to comment, we have computational tools, that's fine, but models is certain problem, because in the last, the second last slide, I marked model with a star. So that needs further development.
Yeah, I totally agree. And I think, in empirical models are, even though they're empirical, they're based out of experimentation, there are certain intrinsic uncertainties that are just random and
Sure.
just cannot be eliminated. And the modeling alone could not capture all that. So there still need to be certain level of, data that comes from real world that can help with that process.
I agree. So usually, I know, our language is full with different names and descriptions. And then nowadays, I always call empirical as phenomenological. Sounds a little bit better. And then,
That's probably a better term, right?
So I'm not a machine learning person entirely, but doing a lot of machine learning, if you only have data-driven machine learning, a lot of times you can still be similar as an empirical model, to be honest, right? Yeah.
Exactly. Okay, waiting for other questions to come in. Anyone else in the audience who wants to ask a question? Yeah, we have a lot of additive people here in the seminar, but work in different areas. But I think this computational material science is something that very few of us have gotten very deep into, very in depth into. So this is definitely a very interesting topic, and I hope, I was originally reaching out to you in the hope that it could be, this talk could spark a lot of inspirations to our people here, because we do see the importance of it. It's a very new, very interesting, and very important.
Sure. Yeah, I agree. And of course, as I said, looking forward to some collaboration.
Hey,
Yeah. Hey.
I had a quick question for you. You were talking about cracking around niobium carbide particles in the last half of your talk.
Yeah.
I was curious, how extensive is this, confined to kind of like the localized area around those particulate, or is this something larger, macroscopic scale? Let's say I work experimentally more on residual stress measurements, and actually I've contacted you too through Garrett Pataki about doing some high throughput experimental methodologies for looking at using laser powder bed fusion to do some of these things that you've done through the DED processes. So very good talk and very interesting. So if you're looking for people to collaborate with,
Yes.
we got folks there. So.
Yeah.
Talking about the cracking, yes, I cannot speak all of the different materials, but indeed for the Inconel 740H and the P91 that we use WAAM process, that is actually a plasma melting. So we did find a lot of niobium concentrating along the cracks, and these cracks are actually a large scale. But then even for the small scale that you're talking about, the micro level, we still see the niobium contributions. My understanding from the fundamental physical metallurgy aspects is niobium carbide essentially, is high melting. So during the solidification simulation, you always can find this MC carbide. So it's very easy to form. Driving force forming these carbides is very high. And not necessarily the idea of introducing this is just causing the problems. I think these materials were designed with a simple idea for the traditional rod material, cast material, is to serve as a thin opinion particle. So during the post-heat treatment, you want to control the size of these MC carbides. Apparently, for the additive manufacturing, you don't get a lot of chances. So once these carbides become to be larger than, let's say, 10 micron or maybe even 5 micron, becomes disaster, because the interface strength we call, phase separation, the particle separation energy will become, kind of distinctly different, because coherency will totally lose. So you don't have a coherent interface for this carbide with this matrix phase. Therefore, you becomes having a so-called microvoid softening area, and then start to generate the nucleation size of the pores. So I think that's the main reason for these carbides. And certainly, we want to making sure that we have a good level control by doing the in situ processing design, but then it has to be involved with the control of the cooling rate and the heating rate. Then is another challenge, because even do the processing design with the experiments is not that easy. However, if ideally we can control with a good level of the cracking, then we can go to the next stage with post-heat treatment. Because in the post-heat treatment, you may be having a good chance where hitting the temperature high enough and then resolve some of the carbides. However, the condition is niobium carbide cannot be too much, because niobium carbide is too high with the melting point, and therefore you have no any chance to dissolve all of these carbides. So if you have such a kind of titanium carbide, you probably have more chances. Resolve these carbides, and then in the solution heat treatment step, you can actually reprecipitate all of these MC carbide, and therefore forming these nanoparticles. That's very important, because then you have the thin opinion particle to constrain the grain growth. And then that is the best part. And certainly for the low temperature, you don't want to have, because at the end, these carbides, MC carbides, were always a trouble. So you want to have different ways to eliminate all of these MC carbides formation. Yeah.
Thanks. Very interesting. Like I said, I'll be happy to talk to you more about this some other time.
Sure,
but
sure.
Very interesting talk. Thanks so much.
Thank you. Let's follow up with the discussion.
Yeah, I do know I have some other questions. I mean, some other thoughts I might wanted to share with you about, but maybe just for the sake of this seminar, I'll save it for a later time, and just check around the floor and see if we have any other questions, since we're being a little over time already. So anyone else have a question? I take the silence as a no, I guess. All right. So with that, I think that's the end of our seminar. I wanted to thank you again, Dr. Xiong, for this very interesting talk. And certainly, if we have any other questions from any of the audiences, they know about your information, so they can probably just send you an email directly. And
Sure.
I'll certainly follow up with you. I have some ideas about I'm working on, there is a paper I'm actually writing about. So maybe, after listening to your talk, I'll check in with you to see if you're interested.
Yeah, please. Yeah. Thank you very much. Yeah.
All right, thank you everyone. Thanks for joining us today. Everyone have a very good weekend, and so do you, Dr. Xiong.
Yeah, thank you so
Thank
much.
you.
Yeah, take care.
Take care.
Take care.
Bye.
Bye-bye.
Bye.